Okay, so lesson 5 is the hinge pin. It is the turnkey. It is the pick your favorite metaphor that means once we do this, there's really no turning back. Lesson 5 deals with the chain rule. The chain rule for derivatives of composite functions. Once we have derivatives of composite functions, there are so many places to go with that, I cannot even begin to tell you. And so on this show, we take a look at the chain rule, which really brings us back to a place where we have to learn how to decompose functions. And if we can do that, we are all good to go. So here's the chain rule in plain, simple, mathematical English. The chain rule says, if y is a function of u, so y is a function of some variable, call it u, and g, no, not g, u is some other function of x. Now, what does that mean if we put this together with this? This means that y is f of g of x. So y is some composite function. If you have a composite function, then the derivative of y with respect to x is equal to the derivative of y with respect to u times du dx. This is a place where Leibniz's notation is extremely helpful, because what really happens is you form a chain and the du's sort of drop out, and I'm using air quotes on that, drop out, because they don't really drop out, but they do. So that's what's going on with that. The other way to say it is that if you have the derivative of a composite function, f composed with g, then what we do is we take f prime at g of x times g prime of x. It's the same thing, it's expressed differently. You take the derivative of the outermost function, so to speak, evaluate that at the innermost function, and then multiply by the derivative of the innermost function. Let's see, do I have the pic? I probably don't have the picture because they wiped the thing. Okay, so last year in our pre-calculus work, we would call that innermost function, we would say, look, guys, it's not really, it's just a chicken nugget. We would say that. And we would say, okay, so you take the derivative of the outermost function at chicken nugget, whatever it is, and then multiply by the derivative of chicken nugget. We would say that. But now we're big people, so we can't do that. So we have to, oh, really? 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 So we have to say, big people talk, f prime of g of x times g prime of x. So what does that mean for us? Here's what it looks like in practice. If the position function for a particle is cosine of t squared plus 1, find the velocity function. In other words, we'll look to take the derivative of the cosine of t squared plus 1. And we, of course, recognize that this is a composition of two functions. The outermost function is the cosine function. The innermost function is t squared plus 1. So in this case, using the parlance of the chain rule, we're going to say that the outermost function is the cosine function. And we're going to use u as the generic variable here. We're going to say it's the cosine function, cosine of u. But u is a function itself. It's a function of t. And again, if we were to compose those, we were to stick this in that slot, we would have cosine of t squared plus 1. So I ask myself, what is the derivative of y with respect to u? Well, the derivative of y with respect to u is negative sine u. The derivative of cosine of whatever with respect to whatever is negative sine whatever. And then what's the derivative of u with respect to t? Well, that's just the derivative of t squared plus 1, and that's 2t. So when I go to put them together, the derivative of y with respect to t is the derivative of y with respect to u times the derivative of u with respect to t, which means that this thing gets replaced by that, and this thing gets replaced by that, and so I have negative sine, I can't write u, I will write instead what u is, times du dt. That's how the chain rule works. We take the derivative of the outermost function, evaluate at the innermost function, times the derivative of the innermost function. So what's that mean? Find y prime if y is the square root of x cubed plus 1. Square root of x cubed plus 1. So again, the outermost function is the square root function. Y is the square root of u. The innermost function, the u itself, is x cubed plus 1. So I ask myself, what is the derivative of y with respect to u? That appears to be 1/2 u to the negative 1/2, because my original function is u to the 1/2, and that 1/2 comes down in front, subtract 1 from the power. What is the derivative of u with respect to x? The derivative of u with respect to x is the derivative of x cubed plus 1. Now I want to put them together. The derivative of y with respect to x is the derivative of y with respect to u times du dx. So I've got 1/2 u to the negative 1/2 times 3x squared. But I can't leave the answer in terms of u. I have to substitute u back in. That is your chain rule. We take, now you could say to yourself, can't I just do this in my head? Can't I know I have a square root thing, so I've got 1/2 thing to the negative 1/2, and then I just multiply by the derivative of that inside. Well, that's where I hope we get to, but if we're not there yet, then please show a decomposition. That'll be great. It'll be great when we do stuff like this. Find y prime if y is the tangent of the square root of x squared plus 3x. Because now I know that the outermost function is the tangent function, but the innermost function is also a composition. I mean, there's an innermost, and then there's like a super innermost. So I've got functions nested within functions. I know that y is the tangent function. I know that u is a square root function. Call that square root of v, just because that's the next letter. And v is a parabola. I have functions within functions within functions. I've got to decompose them all the way. So what have I got? I've got that the derivative of y with respect to u is secant squared of u. I've got that the derivative of u with respect to v is 1/2 v to the negative 1/2. And I've got that the derivative of v with respect to x is 2x plus 3. So when I go to put it all together, the derivative of y with respect to x is secant squared of u. Now I'm not going to write u. I'm going to write what u is. U is the square root of v, but I'm not going to write v. I'm going to write what v is, times the derivative of u with respect to v, and that's 1/2 v to the negative 1/2, but I'm not going to write v, I'm going to write v times 2x plus 3. Mr. Ritter, couldn't we just do it where we said I've got a tangent of something, so I know the derivative is secant squared of that something, secant squared of that something, and then I've got to take the derivative of that something. That something is a radical, so I know the derivative of a radical is 1/2 times kablingy to the negative 1/2, and then it's got to multiply by that kablingy's derivative. Yes, yes you can, and I hope you get there. But if you're not there yet, then you show clearly the decomposition so that you can get the chain rule right. Excellent. Excellent. So that's our chain rule. That's our look at things. As a quick bonus thing, this is totally bonus. If a curve is parametrically defined, then the derivative of y with respect to x is the derivative of y with respect to t over the derivative of x with respect to t. And I say that only because this is an application of the chain rule. It's an application of Leibniz's notation where the dt's essentially drop out and you get, oh yeah, those are equivalent. So if I'm looking for the equation of a tangent to the curve where x equals secant t and y equals tangent t at pi over 6, then I know how this goes. I've got to find the equation of a line, and the equation of a line is y minus y1 equals x minus x1 multiplied by the slope. How am I going to get y1? Well, to get y1, I'm going to throw pi over 6 into the tangent function, and that's going to be 1 over root 3. College Board doesn't care about rationalization, neither do I. How am I going to get the x value? Well, I'm going to throw pi over 6 into there, and I'm going to get 2 over radical 3. Again, College Board doesn't care about rationalization, and neither do I. To get slope, I need the derivative of y with respect to x. That's dy dt over dx dt. The derivative of y with respect to t is the derivative of the tangent function. That's secant squared t. The derivative of x with respect to t is the derivative of the secant function. That's secant t tan t, and that'll totally mess with your spell check. So that all goes away, and you get, oh, let's see, this is 1 over cosine. This is sine over cosine. The cosines drop out. 1 over sine t evaluated at pi over 6, that's 2. That's 2. And so I can get the equation of a tangent line that way. Okay, so the big deal, the big deal. This is the chain rule. This thing matters. This thing is hugely important. I cannot even begin to describe it. In fact, beginning in our next lesson, we look at some of the major ramifications of the chain rule. And we have to spend some hefty time there because they're nasty. Okay, that's it. That's my thought. All right. You've done great. See you soon.